Hello again. This is a Math Club presentation of the Integration B for 2024 solutions coming to you from the College of DuPage. And I would encourage you to use the pause, rewind, or play things if you're interested in really going in detail into any of the solutions. I will go fast. Problem number one introduced the floor function defined up here, and I ask you to evaluate this integral. It's a definite integral, so your answer will be a number. So you use Riemann sums, add up the numbers and take the difference, and the answer should be 6. The next problem involved evaluating an integral, definite integral involving the absolute value. This time you get triangles and you add the areas and you will get 125 over 6. The third problem involved a little bit of thought about the substitution to use for this indefinite integral. You have an index here of for the root of 2, an index here of 3. So that motivates you to consider x equal u to the 6th, and dx then would be 6u to the 5th. You make that substitution, and once you make that substitution, you can do long division. And when you do long division, you get this expression, and you integrate term by term, and you get this. And then you go back to your native variable and make the substitutions. And so this is the answer you get, including your constant of integration. Number 4, I ask you to evaluate this. And the key was recognizing that that's the secant, and we use that time-proven technique of multiplying by 1 in a clever way. And this is quite clever. Then you make the u substitution of u equals secant x plus tangent x, and that's exactly what you want, and you'll get the natural logarithm of the absolute value of secant x plus tangent x plus c. Here you were to evaluate this indefinite integral. And here make use of another tried and true technique in mathematics of adding and subtracting e to the x. Once you do that, you have things that you can handle fine, and your answer is going to be x minus the natural logarithm of the absolute value of 1 plus e to the x plus c. And the absolute values here are optional because that term is always positive. Here you were to evaluate this integral. Surprisingly, I can just let u equal e to the 2x plus 1 whole to the 1/2, and this is what du is, and so this integral really just is the same thing as du. And so this is the answer, the square root of this u. So it's the square root of e squared, or e to the 2x rather, plus 1, plus a constant of integration. In number 7, you were to evaluate this definite integral. You can make this substitution of u equal x plus 1. That means x is equal to u minus 1 and du is dx. And so I just make that straightforward substitution, do the algebra, and do the integration, and return to my native variable, which was x. And so this is the solution, 2 over 5, x plus 1 to the 5 halves minus 2 over 3, x plus 1 to the 3 halves, plus a constant of integration. Here is the problem 8. You were to evaluate this indefinite integral. Changing the sign here is a useful thing to do to make the problem a little simpler. Then you make the substitution u equal tan x du equals secant squared x dx. And then you can use the fact that since du is dx is du over secant squared, but secant squared is tangent squared plus 1, we can change this and we get something nice in the denominator of u to the 4th minus 1, which can be factored this way. And so then what we're going to do is use partial fractions to end up with things that are pretty easy to integrate. And so we integrate all of those with this answer, and then we must return to our native variable of x. And so when we turn to our native variable with x, this is what we get for our solution, and there is the plus c. Problem number 9, you were asked to integrate the square root of tan x dx. Here again, it is useful to multiply by 1 in a clever way, secant squared, and that allows you to work this substitution with this trig identity. And so we have something here that I can now, letting u equals that, and recognizing that secant squared is 1 plus tangent squared, I can make this substitution and have the square root of u over 1 plus u squared. Now, to do something with this, though, you have to do another substitution. You're going to let u equal 2v, du is 2dv, and you go through the calculation, and you get to this point, and things are starting to look a little bit better, but you have to do a third substitution, letting w equal the square root of u. And when we do that, dw is going to be this, and I make all of those substitutions, and what I will end up with in w then is w squared over 4 plus w to the 4th. Okay, now there's a bit of fancy factoring that happens here, and so you want to think about that, because maybe you didn't think about factoring this way, but it will work, and there's the w squared. So after we do the fancy factoring, we can do partial fractions and get this expression, and then we'll integrate this. And again, you should work through the details here, but this integral becomes this, and this integral becomes this, and we're taking the difference between the two. And so we are able to take that and add a plus c, and then we're going to have to go back to our native variable. And there's substitutions galore that we work through, but this is what we get as a final answer. The dot dot dots really just mean I'm going to the next line, and that is plus c. Problem number 10, you were to evaluate this integral. Again, this is the cube root of this expression. Okay, so